Sarah, could you tell me?
The upper right.
Upper right. See, you're increasing as you go across. So these are the high ones, which then of course means this is the hot spot for the low ones. Okay, because this one, of course, we're talking size. That's why I use the term small and large or big. Here we're talking energy amounts. So that's why I said high and low, or change words on it. So let's come over here. Which of these has the largest radius? Now, I said there was a trick that you could rank them in relative positions on the periodic table. And on this one, if you look, probably we could slip by without rewriting them, because they just happen to be in one particular period. We've got aluminum, and then silicon, phosphorus, sulfur, and chlorine. Okay, so this is not a very tricky question. And then, which is going to be the largest of those? What would we say, Nikki, in the second row? Aluminum. Okay, because if I did take the time to rewrite as the periodic table would go, it would be aluminum, silicon, phosphorus, sulfur, and chlorine. We're cutting right across in the same period. By the way, which period is that, Allison? Which period are we at? 3. We're in the third period, going left to right. And here are the facts that we know it decreases as you go across. So our largest is going to be this one right here. And so we could go larger. We could have ranked them pretty easily. You sure you got that greater than, less than business correct? Are we okay on that first one? Okay, now, let's look over here. Rank in increasing order of atomic radii. So now we got to rank them all. And here's where I said the language is sometimes confusing. If you're going to rank them in increasing order, do we want smallest to largest or largest to smallest? Smallest to largest. We want them increasing. Okay, here, since we've got 5 of these guys, it might be good. Let's go relative position. And let's see, I've got a potassium, and then I've got a sodium that's above it. And then I've got a magnesium that's to the side, so I've used up these 3. And then I've got a cesium. Where's cesium? Can you spot it? Where's cesium? Yeah, 1A. It's in the 1A family, also called what family? Alkali metals. Not alkaline with an I-N-E. Alkali, ends in I. Alkali metals. Okay, and then let's see. Cesium is going to be a couple of spots down, like so. And then chlorine in the same period, but over to this side. Okay, here's where the snake trick works. Okay, so we're going in increasing. So we want to get, where's the smallest? Upper right-hand corner. So this is the smallest. This is the hot spot for the small. Okay, here's the hot spot for the big. The snake will work. Okay, now, I think some of you, maybe at break time or something, you were worried, will this one always work? It will work with the ones that I give you. You know, in real life, where you could just have a scramble of just about anything, there would be some tough ones to do this way. But this will work. And on these problems, too, I want to point something out. Let me go back to something I was showing you. The table that's in your drawer. Okay, it was on page 182. The table that we looked at, for you compulsive people that never want to be wrong, if you were doing a review sheet and you think, I'll just turn to this and I will get my answer. Okay, yeah, that's okay, but test data's not going to handle it, because you got to know the trends so you can predict without benefit of that table. And so, let's go for it. Who's the smallest of them all, Nina?
Oh, on the top right.
Okay, and give me a name.
Oh, chlorine.
Chlorine. Okay, is less than. Who's coming next, Andrew?
Magnesium.
Magnesium. Okay, anybody? Who's coming next? Sodium. Who's coming next? Potassium.
Cesium.
Cesium is the biggest of them all. Okay, now if it had said rank them in decreasing order, what clever thing would we do? Flip it. Flip it. Okay, Andrew.
What if it was like chlorine and oxygen? One's lower, one's above.
Okay, what I said is you're going to have a clear-cut call. Okay? That, yeah, I know there's a lot of, well, what is this? What is that? It's going to be clear-cut if you're just using these trends. Okay, now we've actually talked about 2 levels of understanding here, and I skipped the middle one. Here's your first level, know the facts. The third level was actually using the facts and doing a problem. The middle level is how do we explain these trends? Okay, if you're going down any family, it's always a what effect. You could just fill it in as one word, or you could, if you don't know the word that I'm thinking of, what would you say? Anytime you go down a family, the trend is dictated by what? Who was talking? Nikki?
Increasing or decreasing?
Yeah, but what dictates that? What causes that?
The proton, the electrons?
Okay, more about the electrons.
The volume, the shells.
Yeah, the shells. It's a distance effect, and distance was what I was trying to pull out of you, but you may not have thought of that word. But what dictates size? First energy level, second energy level, third, fourth, fifth. Okay? And then, as you go across any of them, we had a pat answer. What dictates that?
The protons get higher, so the electrons are more attracted and they
Okay.
pull in.
Okay, I question your wording. You got the right idea. Protons get higher. It sounds
The-
like
the
you're
numerical,
smoking funny
there's-
little cigarettes.
There's more protons, so
Yeah.
the electrons are more attracted to them and they get in tighter.
Yeah,
and
they're
it actually
sucked
gets
in.
smaller.
So any of the trends that we look at, it's effective nuclear size, or pardon me,
Or charge.
charge, excuse me, I used the wrong word. Effective nuclear charge increases and therefore attracts better. So, let me take from the top. Okay, going down a family, distance, where those electron shells are, okay? Then, going across, it's always effective nuclear charge is increasing. Those are the 2 pat answers. Okay, now, ionization energy. Well, that's nice. I didn't put anything up there. That's a hard question to
I
answer.
used the ones above it.
Yeah.
Oh, did I? Okay.
Cesium.
Okay, so if I want to rank which has the lowest ionization energy, then we come over here. Whoever is physically closer, here's the hot spot. So which has the lowest ionization energy of this grouping? Thank you, Bruce, you bailed me out. I think I really was thinking of doing some others. But Bruce has already answered, it would be cesium. Do you see how, if all it says is what's the biggest, what's the smallest, no sweat, we can pick it out pretty easily. It's when you have to rank that you really have to think. Okay, now, here's another question that's kind of off the wall. And we've talked about this before, but it's going to be important as we go along. The term isoelectronic, if we translated that, how do we translate that? What do we mean when we say something's isoelectronic? Nina?
Like the same charge?
Not the same charge
The same.
now.
No, at the same.
Same number of electrons.
Same number of electrons, and then in a further part, same electron configuration if they got the same number of electrons. ISO means the same, okay? So, this is a multiple choice format. If I have sodium and sodium ions, now remember we're talking same number of electrons as Marco just told us. Okay, are these isoelectronic with each other?
No.
No way. Because this has done what? Lost one or gained one over the atom? Lost one. Okay, sulfur and selenium.
No.
No. Give me a reason. Pedro, give me a reason.
Sulfur has, it's gonna be isoelectronic to neon?
Well, if it took on a charge, but that's not
Oh,
really
no,
an
I mean
issue.
argon.
Well, if it took on a charge, but that's a neutral atom, it's not the ion. So I'm talking about sulfur and selenium. I think perhaps a misconception is you can only say something is isoelectronic with a noble gas. Okay, we can do that, but it's also, you can say, this is isoelectronic with this. We did work one problem. Okay, argon. Cl minus 1 is isoelectronic with argon. Sulfur minus 2 is isoelectronic with argon. However, sulfur minus 2 and chloride minus 1 are isoelectronic with each other. So that's fair to say that. So here, take from the top. I got sulfur and I got selenium. Are they isoelectronic?
No.
No way. Because sulfur would have how many electrons when it's neutral? Anybody, shout it out. 16, but selenium would have 34. No way those guys can be isoelectronic. Trash it.
So they're all different periods.
Oh, yeah, hey, yeah. It's just, do you really understand what this term means? I got sulfur minus 2, and I have selenium minus 2.
No.
No way, same story. Because this one is isoelectronic with what? What noble gas? Argon. This is isoelectronic with what noble gas? Krypton. Okay, now how about F2 and Cl2? Are those isoelectronic? No way. Totally different number of electrons. So hey, the answer must be coming up, right? I have sodium plus 1 and oxygen minus 2. Look at the periodic table. Oxygen minus 2. You're isoelectronic with what noble gas? Neon. Sodium plus 1. You're isoelectronic with what noble gas? Neon. Therefore, they are isoelectronic with each other. Okay, good. Now, we reviewed that a bit, we've reviewed that, we've reviewed that. Now we're ready for this short little section here. This, electronegativity. First, let's have a definition.